Hi, this is a brief overview of our work, Multimodality as Supervision, self-supervised specialization to the test environment via multimodality. On the left, we have the de facto paradigm in machine learning. We pre-train models, such as CLIP, Dino V2, 4M, on a large-scale dataset, generally based on the internet. But if we consider applications like household robotics, augmented reality, domestic digital assistants, we usually need models that are very performant in a specific user space, or as we call it here, the test space. For such applications, we consider an alternate paradigm, where we ask, how far can we go if we learn from the test space only? To put it more concretely, the de facto approach is to take a generalist that is trained on internet-scale data and deploy the same model to various downstream scenarios. In this work, we propose test space training, an alternate paradigm where we pre-train a specialized model in the same space we deploy it in. The approach is fairly straightforward. It first performs unsupervised, multimodal data collection in the test space, which is followed by self-supervised pre-training on this data. Then we evaluate these models by transferring them on various downstream tasks, based on a small transfer dataset from external spaces. We use cross-modal learning to perform pre-training on the data collected from the test space. We implement it using multimodal masked modeling. We start with sensor-based modalities. These can be obtained either directly via device sensors or simple mathematical transformations over it. And we optionally further scale up our set of modalities by using off-the-shelf networks for pseudo-labeling. Specifically, neural network feature maps like CLIP and ImageBind, and output of task specialists for segmentation and detection are used as additional modalities. Now, onto some results. On semantic segmentation, note how predictions from TST are a lot more stable across viewpoints, as compared to generalists' models trained on millions of external images. We refer you to our paper and website for results on more tasks and datasets. Next, we present a consolidated picture of our quantitative results. All models on this spectrum are equivalent in terms of architecture. The lower bound here is no pre-training, so basically scratch, and on the right, the upper bound is fully supervised learning. The gap between them is the playing field for pre-training methods to fill. We highlight two key points here. First, our best method, which leverages multimodality, TSTMM, roughly covers half of the way on this spectrum. Despite being fairly performant, there is still room for improvement by developing better pre-training strategies. Next, if we compare TSTMM and 4M21, the key difference. Here is the source of pre-training data. They both distill from the same pseudo-labels, however, distilling them on the test space data is more performant than on a large-scale external dataset, such as CC12M. Now, we present an analysis studying the trade-off between scaling modalities and scaling dataset size. We start with a model trained for 5 spaces and then scale across 2 axes, the number of spaces the pre-training data is sampled from, and the number of modalities. We find that scaling modalities in the same 5 spaces is more performant than unimodal scaling of dataset size and diversity with external spaces. Next, we present a controlled analysis to measure the effect of specialization in TST. We start with 3 IID or similar, but separate spaces. We pre-train a model in each of these spaces, and then evaluate them across all the spaces. We find that performance is best along the diagonal of this matrix. This suggests that the models have indeed specialized to the test space, as they perform the best when deployed in the same space, as opposed to other spaces. Next, to the specialization-generalization trade-off. For this experiment, we start with a large set of spaces, which also includes our test space. Again, these spaces are IID to each other. We train on an increasing number of spaces and evaluate it on 2 scenarios. The test space, which measures specialization, and a set of held-out spaces, which measures generalization. We find that this reveals a trade-off, whereas we increase the number of pre-training spaces, generalization as expected improves, but specialization to the test space is hurt. Lastly, to support future work in this direction, we have built an iOS app which lets you collect multi-sensory data from any custom space using an iPhone. It lets you collect aligned data from sensors such as RGB, LiDAR, IMU, ambient lighting, magnetometer, and so on. We open source the app along with all our code. Please check our website for more details. Thank you for your attention.